Okay, yeah, thank you so much, everyone, for your patience. I think we can get started. So it's my pleasure to welcome our speaker for today's MLFL. Aviral Kumar is a research scientist at Google DeepMind, based in Mountain View. Finished his PhD from UC Berkeley in September 2023, and will be starting as an assistant professor in the computer science and machine learning departments at CMU this fall. His research focuses on developing effective and reliable approaches for sequential decision making, and towards this goal, he focuses on on designing reinforcement learning techniques and on understanding and applying these methods in practice. Before his PhD, Aviral obtained his B.Tech in computer science from IIT Bombay in India. He is a recipient of the CV and Daulat Ramamurthy Distinguished Research Award, given to one PhD student in EECS at Berkeley for outstanding contributions to a new area of computer science research. He has also been the recipient of the Facebook PhD Fellowship in Machine Learning and the Apple Scholars in AI/ML PhD Fellowship. So in today's talk, Aviral will be talking to us about the challenges in scaling up DeepRL and a potential roadmap for a solution. With that, I'll hand it over to Aviral.
Yeah, thank you so much for the introduction, and thank you for having me here. Yes, I'll tell you about some of our recent work and trying to scale up DeepRL in a variety of domains. This is not at all the solution finally, but at least hopefully gives us some inspiration for what we can do next and how to make this possible. Yeah, so I guess if you have any questions, feel free to please ask them during the talk. I think I would much prefer more like a dialogue rather than sort of just me speaking. If something is unclear, you can also post it on the chat, and I'll periodically check the chat over time.
Yeah, and I guess like just a quick note on that. If anyone has questions, just raise your hand. I'll give you the mic.
Yeah. Okay, so let's get started. So the main topic of this talk is deep reinforcement learning. Now, I guess the conventional motivations a lot of the times when people talk about deep reinforcement learning is an agent interacting with the world and learning by trial and error. To me, I come from a very machine learning background, and I approach DeepRL as a learning paradigm. And to me, there are two properties of DeepRL that stand out, that sort of motivate me to kind of pursue this direction of scaling. The first thing is it's a learning paradigm that, unlike supervised and unsupervised learning, which tries to model the data or tries to model relationship between variables in a data set, unlike those paradigms, DeepRL tries to discover better things than the data. So if you think about decisions or as for instance, labels or actions, DeepRL methods try to discover or try to prescribe techniques to discover better decisions than whatever has been seen before. And the second thing is that by virtue of trying to solve for better decisions, this results in like emergent strategies such as uncertainty reduction, test time adaptation, planning, etc. And these precise properties are basically what makes DeepRL sort of methods unique in this regard compared to supervised and unsupervised machine. So if you think about the classical definition of DeepRL, and this is kind of what we are going to focus on, it operates under this setting where there's a model or an agent that interacts with the world by making some decisions. So these could be, for instance, actions in the case of a robot, maybe natural language responses for language models, etc. It observes some consequences as a result of making these decisions. Typically, these are in the form of stochastic reward signal. And in this talk, we'll consider this to be rewards. You can also have other kinds of feedback here, but just for simplicity, consider this to be rewards. And this world is typically stochastic. So this world is changing its state over time. For example, if a language model is interacting with the user, this is potentially the user's internal state of mind. If a robot is interacting with the open world, this is everything happening in the open world, etc. And our goal now is to be able to train these models to be able to make good decisions that are hopefully better than anything that they have seen before. And in this process, we want these models to be able to discover strategies to reduce their uncertainty, plan on the fly, test time, adaptation, etc. In a more sort of machine learning terminology, this learning paradigm has to deal with two problems of objective shift and distribution shift. So when you typically think about trying to optimize for the best decisions or finding best decisions than what you have seen before, presumably you have to deviate away from anything that you have seen in your data, which means that fundamentally you will have to suffer from distribution shift in some way or the other, or you'll have to deal with that in some way or the other. So what DeepRL algorithms often do is that they operate under this regime of distribution shift. And secondly, a lot of the times it's unclear what it means to optimize for the best decision directly, because oftentimes utilities are delayed, in which case you have to find surrogate objectives and optimize them. So you deal with objective shift. So at a high level, all the things that we'll be talking about today are really developing techniques to address these two challenges of objective shift and distribution shift. Or in some other ways, these are challenges that emerge because of these two challenges that we talk about today. Okay, so with that, we can sort of just look at a quick example that I think is particularly quite neat to kind of motivate why we need deep RL. And this example is a very simple example of, for instance, things such as chip design. So in this case, let's say I gave you a data set of some chip designs and some runtime values associated with these chips. Some of these chips are good and bad, meaning some of them have a really low runtime, some of them have a really bad runtime, meaning a really high runtime. In this problem, you would often want to discover a chip that is better than your data. And this is, in my opinion, a reinforcement learning, more precisely a bandit problem, where simply doing supervised learning or unsupervised learning is not enough, because these paradigms, they end up modeling the distribution of variables in your data. They don't end up finding something that is better than your data set. And this is precisely what I was referring to in the on the previous slide as the benefits of deep RL. It is a learning paradigm that allows us to discover something better, because it solves problems such as utility maximization that you can see up here on this slide. Now, in a sequential setting, you will get all these emergent properties of uncertainty reduction and so on, which I'm not talking about today. But this is sort of the 101 problem that at least seems to motivate deep RL as a researcher. So let's come to the topic of this talk today. So the main question that we are focusing on is, how can we scale up deep RL? And the way I've been thinking about this problem is to take inspiration from standard sort of scaling up of generative models and NLP and vision, where these models are typically trained in a phased pipeline. There's a first phase where you do pre-training. You train on lots and lots of diverse data with the highest capacity models. And then there's a second stage of task-specific adaptation or fine-tuning, where you fine-tune these models to your desired downstream task. So the roadmap for scaling up deep RL that we'll follow is something that also operates in these two phases. In particular, it would try to take a lot of data from sources that already exist, including data sources that are particularly not relevant for your problem. Use it to train a model using reinforcement learning methods, or develop techniques to train such models at scale with reinforcement learning. And then once you're given access to some environment for your target deployment scenario, you would fine tune these models or adapt these models on the fly with potentially some interaction with the world, continuous adaptation, continuous learning on the fly upon deployment. So if we take this picture, what would this need? How can we achieve this? How can we get the best possible techniques in this picture? So to build towards that, we can partition this picture into three different questions that we can independently try to answer, and then combine together the best of the answers for each of those questions to realize this whole part. The first thing is the question of data. So how can we learn from data sources that are out there, potentially even arbitrary, unrelated to your problem at all? How can you use that to learn good decision-making models or good decision-making policies? So for example, you would want to use, for instance, video data, internet scale video data for training robot policies. Video is not at all the same as video of a robot. It's really video of humans doing things, but can you still utilize it? That's that kind of a question. Or for instance, if your goal is to solve a coding or a math problem, can you still utilize conversational text to be able to solve it? Things of that sort. The next question that comes up here is scaling, which is, let's say we find out a way to use all the data sources. How can we make sure that all the objectives and algorithms we use are amenable to be utilized at scale with many, many parameters than what you can typically than what we typically train on in smaller research scale settings? So how can we scale up these methods? And finally, sort of adaptation or developing techniques and algorithms for being able to fine tune these models to sort of target tasks within a limited amount of online or offline interaction, where sample complexity is the key priority. So how can we do this? So these are the three questions that I think if we can independently answer, we can potentially get a method that can scale up deep RL very, really well. And we've done work on all of these questions a little bit here and there, but today I'll be talking about two of these, which is the scaling aspect and the adaptation aspect. So how can we scale up RL methods to train large models? and how can we fine-tune large models with reinforcement learning type techniques. Um, Okay, so let's start with the large models part. So this section will be based on three of the papers. One of them just came out on archive like a month ago. One of them appeared in iClear in 2023, and one of them is a more theoretical paper from 2022 back in the day. Okay, so I want to first motivate why we are studying scaling, parameter scaling, particularly in RL. So when we started doing this line of work, that was 2022, and one of the papers that people were building a lot on, at least in the RL community, I was hearing a lot about this, was the SimClear paper. And this picture that you see up on here on the slide is a picture from the SimClear paper. It's I think they're figure 1. It shows how for self-supervised learning, they're plotting the ImageNet accuracy, top 1 accuracy on the y-axis as a function of the number of parameters in the model. So this was still back in the day when millions was really high and not hundreds of billions. But in this case, if you, so these are a bunch of self-supervised learning methods. The exact names are not very important. But in 2022 or 2023, actually, prior work in RL was always operating at the regimes of training networks that lie in this regime, which is shown by this gray colored box. So it's always parameter size less than or equal to 50 million or so parameters that you can see up here. So what we did in this line of work so far has been to the initial part to push this frontier up to about 100 million parameters, and then more recently to push this up to 400 million or so parameters. Now, of course, these are not on the same problem domain, but at least we are able to train models of this size reliably with RL now using some techniques that I'll talk about next. There's still a long way to go though, because we are still in sort of millions. There's a lot of things that can be done with billions really, really well in this case, if you want to pre-train or train entirely from altogether. Okay, so I'll start by describing the initial work that we did, which pushed the scaling frontier up to 100 million parameters. And this work was set up in this problem domain of training multi-game Atari policies. So for those of you who are familiar with deep reinforcement learning, Atari games are a very standard benchmark in this domain. So there are these video games where people typically train policies to play these games one game at a time. So in this line of work, what we did was we tried to train not just one policy to play each game individually, but rather a single model that can play all of the games together. The reason why this was something that we studied was because we already know Atari games were sort of an easier domain by the time when we were doing this work, one game at a time for RL algorithms. But large-scale training across all the domains was actually quite problematic. So large-scale training across all the Atari games was problematic, and that's what we wanted to test. So this was sort of the test 101 for being able to train large capacity models in this domain, and that's why we started off from this. So to be more concrete here, we had about 2 billion data points given to us. We had 40 games, so data from 40 games, and this data was suboptimal data. And we wanted to take all this data now to train a good policy to begin with, a generalist policy to begin with on these games. So if you take this domain, and there's this prior work that is cited up here on the slide, which tried to do imitation learning style approaches on this data. And what it found was imitation learning approaches. So this is filtered imitation learning or decision transformers. These methods ended up exhibiting quite favorable scaling trends when you scale up your model size from a small model to a large model. But RL methods, in particular, in this case, offline reinforcement learning methods, because we are taking data that exists and training on top of that data, offline RL methods ended up exhibiting much less improvement as you scale up model capacity. And if you scaled up model capacity a lot, your performance started to degrade compared to the model with a smaller capacity. So clearly something seemed wrong here, where we didn't know what's happening in this case. So we sat down and we started to kind of look at what we can do here with how can we enable scaling of Q-learning methods. And we took a very systemsy approach in this case, where we wanted to get something that allows us to get some initial signs that showed offline RL methods can actually scale really, really well. So what we found was 3 ingredients were key for scaling up offline RL. The first one was the choice of the offline RL algorithm. So there are many ways you can run offline RL, or more generally even reinforcement learning. But the choice of the algorithm was a key factor. And one of the things that we found here was that we needed to use the conservative Q-learning algorithm, or CQL. It's an algorithm that looks a lot like deep Q networks, for those of you who are familiar with that, with an additional regularizer that accounts for the fact that you are dealing with offline data. Um, that's sort of the high level gist of this approach. The second thing we needed was a large neural network because we needed a higher capacity model. In this time, we were still using ResNets because that seemed like the natural increment from a very small convnet that people were studying on Atari domains to sort of graduate from there to a ResNet. There were a few design decisions that were important here, such as you needed to change the exact form of normalization in the ResNet. You need to make the ResNet output be cognizant of the positions of different pixels and where some signal comes from, unlike classification problems where you just care about existence of a particular feature in the image and not where it exists. Whereas for control, you kind of need where it exists. So things of that sort. So there are a few architecture design details that were important here that we did. And finally, what we found was we needed to be able to effectively use model capacity. So this is actually a big issue that happens with deep RL methods, that a lot of the times the updates that you do with Q-learning approaches tend to be very different from the kind of updates you would do with supervised learning, such as just optimizing for likelihood. And when this happens, you often end up not using the capacity of your model, the parameter size of your model effectively. So you need to be able to put the appropriate regularizations in place so that you can use the model capacity in a favorable manner. And we needed kind of two things here that were important. The first one was the need to use some normalization, which I've been calling DR3 normalization. It normalizes the features that you learn in your network to have a norm of 1, or a small norm in general. In this case, 1 just seemed like a constant number we can fix it to. And the second one, which was important, was you needed to be able to discretize your Q values when you run your Q learning updates. So typically, when you do Q-learning, you would pose Q-learning as a regression problem. You're training a continuous estimate of your long-term reward. That's your Q value. You're now, in this case, although we ended up representing this Q function as a categorical distribution using distributional RL approaches. And then we applied a cross-entropy, a categorical cross-entropy loss. So these were two things we needed. So let's go a little bit deeper into what each of these things were in this case. So the first thing was this normalization. And this is something that we did earlier in 2022. And the key thing that we were trying to understand was why, so the way we came up with this regularization or normalization was while we were trying to understand why it is hard to use large models with RL or with offline RL methods. And to kind of understand this, I'll give you a little bit of our thought process behind coming up with this regularization scheme. I'll not go into too much details of the math here, but at least some high-level intuition. So what we wanted to do back then when we were building this regularizer was to understand why it's hard to use large models with RL. And to answer this question, we tried to understand why it is easy to use large models with supervised learning. Turned out that like one theory that exists out there, which talks about why large models can work well with supervised learning, in particular over-parameterized models can work well with supervised learning, is this theory of implicit regularization. So what does this theory say? So in a nutshell, this says if you're minimizing some loss function, a supervised loss function over some over-parameterized loss landscape, meaning you have many more parameters than how much you need to fit your data. In such a scenario, you would, if you solve this optimization problem using gradient descent, in particular stochastic gradient descent, you're going to be able to get a solution that does not just minimize this loss L theta, but that minimizes L theta plus a regularizer that quantifies the preference of your optimization procedure, in this case gradient descent, towards finding certain solutions in your parameter landscape. This regularizer is called the implicit regularizer, and it's simply induced as a function of your objective of your optimization procedure. So think of it as this: that let's say you have many possible theta values that minimize your loss. You're not going to converge to arbitrarily any of them because your optimization procedure, the gradient descent algorithm, has an affinity towards finding certain ones or preferring certain ones over certain other minimizers. And this regularizer is just something that quantifies that preference in the form of an optimization problem. Now, in supervised learning, it is kind of known that like this implicit regularizer, or it's at least widely believed that this implicit regularizer prefers simpler solutions or more regularized solutions. So when you've heard about things like you might have a lot of parameters, but you don't actually overfit on them, that's at least one theory that people believe in is the fact that this implicit regularizer is the contributor that prevents you from overfitting on your weights. And those simpler solutions, these less overfitted solutions tend to generalize better in practice and work well. So we said, okay, well, if that's the case, then that we have one theory or one mental model of why supervised learning can work. So can we go back and try to understand what's happening with offline RL in this case? So what's the implicit regularizer in the case of offline RL methods? So we did exactly that. In particular, we considered, if you train a value function or a Q function, Q of state comma action, X comma A, it's a neural network. And let's say you define the last but one layer output of this network as your features, phi theta of X comma A, theta are the parameters of this network. You can write down the closed form solution for the implicit regularizer in this case. And of course, like this relies on a number of assumptions. And there's a number of assumptions that exist out there in literature studying implicit regularization for just general supervised learning. We built on one such work, which shows that for supervised learning, if you were to train this model, this Q theta X comma A, using just a standard supervised loss, you would get a regularizer that minimizes the norm of the feature. So it tries to learn, you can think of this as weight decay, but not on weights, but rather feature norms. So it's like feature norm control. That's what this regularizer prefers. If you extend this analysis to offline RL, you would get that now with these Q learning methods, you have a much more complicated regularizer. So the first term is still the same. It's for RL methods, the RL objectives would still ask you to reduce the norms of the features, which is a good thing because presumably that helps you in supervised learning because it appears in the regularizer for supervised learning as well. But there's a second term which actually plays a counterintuitive role in the case of RL. So if you think about this, again, there's probably a lot more deep argument here, which I'm not going to go into. So I'll give you just some high level intuition here. This regularizer, the second term in this regularizer has a negative sign in front of it, which means that if you minimize R of theta, you're going to maximize the second term. The second term, if you look at it more carefully, looks a lot like the dot product between the feature vectors for some X comma A and some other X comma A's. So these are two different state action pairs and passed as arguments to this feature function. When you are minimizing this regularizer, you are maximizing the dot product of these features, which means you are essentially trying to increase their lengths, increase the lengths of the features, because maximizing the dot product can be done by either increasing alignment of the two vectors or by increasing the magnitude of the two vectors. And that's what is happening here, where you're kind of trying to do both, but then you're also trying to grow up the magnitudes of the vectors, which is in some ways or the other conflicting with the first term, which is trying to minimize the feature lengths. So in some way, this like implicit regularizer theory suggests that while in supervised learning, you're learning these simpler low magnitude features that at least empirically seem to generalize really well, in RL or in offline RL particularly, you have this additional term which is trying to undo this phenomenon actively. So with this in mind, one of the things we did was, well, a simple approach to kind of preventing this term from existing or preventing this term from being really active was to control this term explicitly during RL. One way to control this term is to add this back as a regularizer. So you can simply say, I'm going to run RL, but I'm going to add this second term as an explicit regularizer to my algorithm. So even if the implicit regularization effect prefers solutions with a high dot product, my explicit regularizer is going to cancel that. But the other way, which we found more kind of compact and easier to tune in the scaling setting, was to simply constrain the norms of the feature vectors. And that's what I referred to earlier as this feature normalization approach, or DR3 normalization approach, where you would simply make sure that the feature vectors cannot have a norm more than one. They have a norm exactly equal to one. So while the dot product can still align feature vectors better, it can't grow the magnitudes of these feature vectors unbounded. It's an invariant that is now satisfied by your neural network exactly, and so you can't change it at all. So that is the first idea, which is you normalize the feature vectors to a norm of 1 exactly. You can also penalize, you can also add this as a regularizer. In that case, you'll have to probably tune a multiplier on this because it's a regularizer. For example, if you add weight decay to your model, you'll have to tune the coefficient of the weight decay term. Likewise, you'll have to add, you have to tune the coefficient of this regularizer if you add this as a regularization. But you can also do this as a normalizer, which is what we did in this scaling. So we found that this actually helped us a lot. And turned out that if you simply look at scaling trends, combining all of the pieces that I described to you earlier, we found that this approach that I'm now calling scaled Q-learning actually scaled up over parameter size quite a lot better than just normally running RL that existed with the same model architecture, or even using different model architectures that were very common in the RL literature, which is this Impala shown in green here, whose performance actually degrades if you scale up model size. So there's a set of design decisions that seem to be crucial here, including the normalization, including this loss function that we were using with distributional RL, which is the orange colored line compared to the blue colored line, and the exact architecture that we're using, because the resonance we were using seemed to be better, much better at scaling than if you were to use Impala. So this was sort of one of the first results where we showed that offline RL methods, offline Q-learning methods in particular, can actually benefit from a positive scaling trend as you scale up model capacity. And the DT, this little star that you see up here, DT, it's a decision transformer approach. It's based on imitation learning or conditional imitation. Any questions here so far? Okay, great. So far what we talked about was basically this approach, which tries to use an offline RL algorithm, a large model that was designed in the right way, and two things to effectively use capacity. One is feature normalization, so that the loss function that you're using does not end up blowing up feature norms, which seems to be harmful because it does not happen in supervised learning. And the second thing was the use of distributional RL updates, which are basically updates that would discretize your continuous Q values and then do Bellman backups on these discretized values. It's more nuanced than that, in the sense that like this distributional RL update changes the exact loss function that you would use for your RL algorithm. But this was something that seemed to be quite relevant in this case. So with that in mind, so we had some initial good results. So what we were trying to do then was to scale it up furthermore. So can we scale up further to new domains? And one of the things that seemed kind of limiting here was the choice of the objective. So this piece about distributional RL that I was describing to you earlier, this seemed to be, so initially when we were doing the scaling work, we thought that this was not as important. We simply used this because because it seemed like a more performant approach. But the more and more we try to scale up RL, we actually realized that this distributional RL piece was playing a crucial role. In particular, we are not sure if it's because the distributional RL update prescribes a different loss function, or because it utilizes a categorical cross entropy loss or a discrete representation of the continuous Q value as a categorical distribution. So there were multiple confounding factors here that we didn't know what they were doing. And in fact, you can actually even show theoretically that distributional RL approaches would add a bias in your training process, which means that they should be worse than standard RL methods. But somehow we found always that distributional RL was kind of critical to enable any kind of scaling behavior. So in this next piece of work, what we wanted to do was to kind of dig into this phenomenon a little bit deeper and understand why these methods are actually working. Like, what about distribution RL actually makes scaling easier with RL approaches? And one of the hypotheses we had was that perhaps the key piece that makes the scaling easier is the piece about utilizing a categorical cross entropy loss instead of a regression loss for training the Q function, training the value function. Why was this hypothesis? Because if you just generally look back at the success in machine learning, you find that a lot of the successes have been driven by, or a lot of the successes we have seen, a lot of scaling up successes we have seen have utilized the categorical cross entropy or the negative log likelihood sort of a loss function compared to a regression loss function. So this was a hypothesis that we had in mind, and we wanted to simply explore to figure out whether this is actually true, even for the case of RL. Would cross entropy actually help you in scaling up RL further? So more recently, we released this paper in arXiv where we try to do a much larger study of scaling across a bunch of domains. So not just on these Atari games, but across many other domains. And we found that combining or we found that utilizing the right form of a categorical cross entropy loss actually is something that enables or that boosts up scaling performance a lot more compared to the more standard RL objectives of regression. So here I'm showing a sort of a summary result plot over a single task RL scaling with mixture of expert style models. This Atari game results with this generalist policies that you can see up here, as well as sort of many other domains in robotics, language agent tasks, as well as the game of chess, where we find that you get a lot better scaling behavior if you use a categorical cross entropy loss. In particular, when we were approaching this research, we started with designing some cross entropy objectives. So we took sort of a very basic stab at converting a regression problem, regressing Q values to some target values, into a classification problem. And the simple approach was to kind of just do the very naive thing. We said, well, if we had a set of bins that cover the range of possible values that we care about, we can convert the scalar value, or we can represent the scalar value as a categorical distribution over two bins that fall into this region. So let's say you have a scalar value. You want to discretize this into a categorical representation. You can simply represent the Q values, represent this as a distribution which puts probability mass in two bins, which are the bins that are adjacent or that cover the scalar value that you care about. So you can do this. This is what I'm going to be calling the two-hot approach. But turned out that this approach actually didn't seem to work very well. And part of the reason was that this two-hot approach ends up giving rise to very sparse categorical distributions, because the probability mass here is only non-zero on two bins compared to multiple bins, which is too sparse in some way. We also found that this two-hot approach does not quite respect the ordinal structure of the problem, where different values in the space, like if you consider a value that is right to the left of Z3 and something that's just next towards the right of Z3, these are quite close to each other because these are continuous numbers. For example, this is a number 23.1 versus or 22.9 versus 23.1. These are very close by numbers. But once you discretize them, this notion of similarity is kind of lost. P2 is as far from P3 as P4 or P5 is from P1, because these are just unordered set of bits. So to kind of make sure that we can bake in this ordinal structure, as well as to remove the sparsity problem, you can think of an approach that relies on label smoothing, where you would take your target value, add some Gaussian noise to it. So now it looks like a Gaussian distribution. And now you discretize this into bins. So presumably, if things are close to each other in this numerically, they'll get some probability mass, which is going to be non-zero. It's certainly going to be very biased towards exactly the bin where Y lies. In this case, it's P3, but it's still going to be more smooth compared to just having probability mass in two bins, which has abrupt cliffs in that. And turned out that this approach, which I'm calling a histogram loss, because it resembles a histogram when you discretize it, and Gauss for the Gaussian noise being added here. So this HL-Gauss approach for converting scalar values into categorical distributions on which we can apply a categorical cross entropy loss. This approach seemed to do really, really well in our experiments. So just to kind of recap, the key here is you wanted to convert a scalar value because you have a regression problem, you have a scalar continuous target value. You wanted to be able to convert this into a categorical distribution. You can do it in this two-hot approach, which converts a single scalar into a distribution, or you can do this with this more nuanced approach that converts the scalar value into a noisy distribution, does some kind of label smoothing, you can think of it in that way, and then converts it into a distribution. And we found that this sort of an approach actually seemed to better scaling behavior and better performance in general. Any questions on this approach so far? Okay, sounds good. So now I'm going to show you a bunch of results across.
There's one question.
Yes.
Hi. So it looks like by doing this, you're also probably adding a lot of regularization, because you're saying there's essentially some chance that the Q value could take all these different values. So do you think that part of the success of this approach has to do with regularization?
Yeah, that's a good question. Yes, I think in some ways or the other, it is adding regularization, and part of the success has to do with at least label smoothing in some way or the other. The key thing here is we did try actually taking regression updates, so just the regular mean squared error style updates, and adding target noise to it. We've not been able to get that to work. I'm in some ways that should be the same as basically doing something like this, because you're adding a similar Gaussian noise to the targets. So I'm not sure like if just adding noise here explains the entire success of this approach. Clearly, it helps you get a lot better with scaling compared to too hot approach, which doesn't add any noise. But yeah, I think that's not the full picture. So the precise choice of the categorical cross entropy objective is also important.
Yeah, very interesting. Thank you.
Okay. Any other questions?
I had like a question on the similar part. So
Yeah.
isn't this similar to like assuming the output is like coming from a Gaussian, and you could do better by assuming like it's coming from a mixture of Gaussians than just single Gaussian? Or would
I
that
see. Okay, that's a good point. Yeah, so we haven't tried the mixture of Gaussians part. At all, because we simply kind of added this Gaussian noise in this case. You could do other kinds of, so we also tried preliminarily, we also tried adding Cauchy noise to the target values and then using them for converting it into a categorical distribution. But I think we didn't find like a huge difference. In fact, the Gaussian version was, if only, just a bit better than the Cauchy version. We haven't tried mixture of Gaussians, so that could be interesting as well. I think it's a little unclear for me if how you would convert this into a mixture of Gaussians, because your target value is a scalar number. So you'd probably have to like fit a mixture of Gaussians in the right possible way. But if you can fit it, then yeah, I think then you can potentially use that too. But still, the key here is like I think the choice of the objective that you use for training your model, that objective being that objective being a regression loss, does seem to still hurt quite a bit, even if you like could add noise to your targets. So that objective needs to probably change to a categorical cross entropy. And now the way you convert your scalar values into a categorical distribution could probably benefit from like better ways of adding noise. So that's the high level.
Yeah, thanks.
I think there's one more question.
Yeah.
Hey, I have a question. So, what's the standard deviation of this Gaussian right here?
I think it's 0.6. So it's parameterized in terms of the width of the bin that you are dealing with. So we do it in a way that like so I think this picture is a little unclear. We do it in a way that like the two bins adjacent to the bin where Y falls in, both of them get some probability mass. So they're within the 95% confidence interval. So I think that's the high level basically. But I think this depends heavily on the bin width. So we parameterize it in terms of the bin width so that you don't have to choose a static number for all the domains, because the bin widths might differ heavily based on the ranges that you care about, like Vmin and Vmax, because you have to have the right range of values to be able to discretize a given value into that range, which will dictate the bin width and the bin and the number of bins. So I think it depends. It's a parameterized number of that. But the two bins are just
Sorry. Yeah. So one follow-up question. So how do you discretize the key values? Because I think the range is pretty large, right? So how do you choose like how many bins would be a reasonable number here?
Yeah, that's a good question. So far we've been doing. So certainly I think like if you choose a very large number of bins, then things are very fine, and at that point like you probably don't get as much benefit from this approach. And likewise, if you choose bins to be really coarse, then also things will not work out very well. One reasonable heuristic is to look at Vmin and Vmax for the problem. So that's the maximum possible range of your Q function and minimum possible or maximum possible range in which your Q function can lie. You can compute that by so if you're familiar with RL, like you have a discount factor gamma, you can look at the maximal reward divided by 1 minus gamma and use that as your maximal Q value, and R min over 1 minus gamma as your minimum Q value, and discretize this range. So that's the one way. Now, how do you select the number of bins? I think we've been sticking to 40 and 50 bins basically. Why 50? Because distributional RL used 50 and that they found it to work really well. So we have actually not changed from it. So that's kind of the high level in this case. Now, of course, I think these are still hyperparameters. They are not like exactly fixed, but I would imagine that practitioners will have a rough sense of like what the range of values will look like. So,
Perfect.
yeah.
Thanks.
And one other thing on that note actually is, I think we never got to trying this out, but you can also imagine potentially discretizing this in a way that each bin has a different width, if you wanted to. That'll require a lot of changes to the approaches that we are building on. But there's a lot of work on like autoregressive in autoregressive models. There's a lot of work on like discretizing in the right possible way, potentially using quantile discretization, CDF-based discretization, etc. I think there's a lot of things that can be done there, which we haven't tried. Certainly the methods will not transfer directly, but I think there's also something worth doing there. So you can take your data set and look at some statistics and find and fit based on the CDF of the reward values or of the Q values in your data. Yeah.
All right. I don't think we have any other hands up right now.
Okay. Sounds good. So yeah, so what we found was we found this to work really well across a number of domains. So this is the Atari experiment that I was describing earlier. So the HL Gauss is shown in light green in this case. C51 is the approach I described earlier with the regularization and cross and distributional RL loss. Now, if you replace it with this cross entropy loss based on this label smoothing histogram loss, it does much better. It also does better at a smaller scale in this case. You also find much better results with robotic manipulation. In this case, it's built on top of this prior work that we did called Q transformer. The idea here was you want to train a transformer policy, which can learn from not just like human demonstrations, but also data collected when you're evaluating robot policies, evaluating imitation learning policies. Some of that data actually fails, but you still want to use that data for improving your model. Again, you find that you can learn quite quickly and converge to a much better solution. We also did some experiments on chess. So here, this actually is building off of a recent paper that came out from DeepMind, which tries to basically get a policy for playing chess at the grandmaster level without needing any Monte Carlo research or planning. What they do basically is they take a bunch of games and then try to learn an offline value function from this, and then would take an action based on this value function. We did this exactly with now the HL Gauss loss. This work actually coincidentally found that like regression did not work very well for them, but they converted or they represented in an approximate manner the Q values as a one-hot distribution. So they discretized the Q values into a bin, so there's some approximation error there. But they found that actually was much better if you scale up parameters compared to if you use regression. And what we would be doing is like actually doing a much more nuanced version of discretization. So we didn't know about this work happening concurrently, but turns out that if you just replace the loss with this HL Gauss approach, and by the way, in all of these models, you already have the normalization in the model because transformer models have a very similar normalization compared to what I was talking about earlier. So all of that is already there. So the only missing piece was the kind of the loss. And if you do this, you will find that you can beat performance. You can match the performance of AlphaZero, which uses MCTS now with just a slightly bigger model trained entirely in an offline application. We also found it to work really well on LLM agent tasks. This is sort of a simple tasks, but playing the game of Wordle. Again, here the performance was less sensitive to hyperparameters, and I think this is with a 125 million transformer. So yeah. One other thing that potentially was very interesting for us here was to understand why this approach is working. And what we found was, so there's no single problem that this use of cross entropy, categorical cross entropy addresses, but it addresses a number of, or it makes progress along a number of challenges that plague RL methods. So the first one was this challenge of representation learning, where, as I mentioned to you earlier, like implicit regularization and potentially many other factors, they do affect the kind of representations you learn with when you train Q functions with RL. And one of the things we saw earlier was this blow up of feature norms. One of the other things which people often measure to evaluate the representation quality is to look at how well can the representations learned by a model, how well can they represent value functions for other policies that you might see during the course of learning. And what we found was if you take this metric and you look at how exactly you can represent Q functions for multiple policies well, meaning you do this linear probing style experiment on top of your features that you learned, you'll find that the HL-Gauss approach gives you the best approximations for these Q functions of other policies over the course of learning on top of just these fixed features you learned. So clearly, this HL-Gauss approach is giving you better features than just mean squared error or C51. And note that in all these cases, you do have access to, you do have the normalization thing that I was describing to you earlier. So this is in some ways like extending beyond it and addressing the problem even better beyond something like that. We also looked at the hypothesis that potentially this is actually helping you because of non-stationarity. Potentially regression losses or just mean square error losses are not very robust when your value magnitudes are changing really, really well. So here's a experiment where we try to essentially do some synthetic regression tasks, but we periodically over the course of training, so x-axis is the course of training, we periodically change the bias in my or the bias of the regression targets I'm trying to regress to. And in all these cases, what we found was L2 regression or MSE regression is it becomes harder and harder for this sort of an approach to match the magnitudes of the values or the regression targets that you're trying to learn. Whereas with all these cross entropy losses, perhaps somewhat more expectedly, if these values are in the right range, you will be able to quickly adapt your distribution to represent the higher magnitude value function. So they're just better if your value magnitudes are changing. And this is something that happens in deep RL because we are trying to learn for the maximal reward Q function, maximal rewarding policy or maximum Q function policy, which means that the Q function is becoming higher and higher because it's trying to estimate the Q value of the policy, which itself is getting better. So its values are increasing and you want to be able to keep up with that, and seems like cross entropy can do it better. In fact, if you also simply just don't have distribution shift altogether, so if you simply just do policy evaluation or SARSA compared to offline RL with this Q learning approach, you'll find that actually for SARSA, it doesn't quite matter whether you use cross entropy or mean squared error, but for RL, it does matter. So when you have more non-stationarity due to distribution shift, due to your magnitude of values changing, you kind of benefit from using a cross entropy loss in this case. Okay, so just to summarize this part, I think I probably am running a little late, but just to summarize this part, the key challenge that we've seen over and over is that if you simply do RL naively, or at least take the recipes that we have built so far naively and apply them in the case of apply them with large models, you'll find that it's not quite easy to get them to work. But then I think at this point we have some understanding at least of what is probably the bottleneck. So this includes things like the bad part of implicit regularization that I described to you earlier. That's one mental model of understanding it. The choice of the objective, that seems another or somewhat orthogonal cause as well, or orthogonal as well as something that's related. So both of them. And that also seems to matter a lot. I'm sure there's many other factors that also affect this more. But at a high level, it seems like if you can understand these pieces independently using maybe toy examples or mental models, we can start to build methods that can actually scale up much better with model sizes. There's still a lot to go, but at least seems like we are being like these methods can inspire solutions that push the frontiers of scaling for RL methods out there. Okay, any questions so far? Okay, yeah, so I guess I had one full part of the talk remaining. I guess I'll go over some of the parts pieces of this, and I'm happy to take questions later over email if I'm not able to finish this. But yeah. Sorry, is there a question on the?
Yeah, there's one question. So if you want to take that right now.
Yeah, let's take that right now. Yeah.
Okay, cool.
Just a quick question. Like, you have Bellman equations for the C51 case and for the MSE loss. Do you have a similar Bellman equation which will show convergence for the HL-Gauss loss?
Yeah, that's a very good question. So I think not exactly because there are still some masses on bins that make it not mean preserving. So HL-Gauss loss, the Bellman equations is Bellman equation is nothing but the. So in principle, the any such discretization should admit the same Bellman equation as you would if you just were doing like the standard RL backup, like the expected RL backup. So that should be the same. With the HL-Gauss discretization scheme, I think there's some edge cases where your probability mass at the boundary of bins is lost, or basically the HL-Gauss transformation is not mean preserving exactly. which technically, in my opinion, I mean, technically, for the sake of regressness, would end up biasing your Bellman equation in some way or the other. We didn't find that to be a huge issue in practice, but in theory, it is probably an issue. I think there's probably ways to address that by using Kramer projections and things like this. But that's not something that we investigated. I think it seemed overly complicated for potentially much lesser headroom in practice. So to answer your question more directly, basically, yes, it's not exactly. I think the practical implementation is not exactly going to give you the true Q function in the worst possible case slash in theory. But in most of our experiments, or in all of our experiments, we never found that to be an issue. But we also know of a way to address this with the Kramer projection. Basically, pretty much how we went from the categorical distribution RL to the Kramer-based quantile regression style RL methods. Basically, something very similar. Like you can use the quantile representations now to fix it. But yeah, not precisely.
Thanks.
Yeah. Any other questions? This part?
No, I think we can go on.
Okay. Yeah. So yeah, I think like we have 7 minutes, and I don't think I can finish the remaining piece in 7 minutes. So let me just tell you some other things we've been doing, which is very unrelated to something like this, but it fits into the adaptation and fine-tuning sort of side of things. So so far what I was talking about was sort of like learning from scratch with RL. But another use case that we have for RL, as I was describing to you at the beginning of the talk, is to be able to fine-tune models with RL, fine-tune large models with RL, especially when you are interacting with the world. Now, this fine-tuning would generally be online because you want to interact with the world and learn from the fewest samples possible. This fine-tuning has to respect the fact that you've already done some pre-training on the model. With RL, without RL, that's something we can figure out. Ideally, in the long run with RL, but right now probably a lot of it is just normal next token prediction generative modeling. So the key question now is how can we fine-tune these models with RL style approaches? Again, this has to be done in the regime of large models. This has to respect the kind of function approximators we deal with, which is these transformer-based models in a lot of use cases now. And in this case, I think there's some unique challenges that come in. So what another line of research that we've been trying to do is trying to figure out, trying to build recipes for running RL optimization with these kinds of large models. And we did something that we released in archive just a month ago on like trying to fine tune LLM agents with RM, so large language model agents. I think the same principles apply to any sort of transformer based models, transformer based policies in any domain, including robotics. And some of the students who are working with me are actually looking at extending these ideas to those domains as well. But then there's also some more general algorithmic work that is listed up here in the slide that I think I don't have time to cover at all. So if you have any questions, I'll be interested in discussing more on email. But let me give you a quick glimpse into this like LLM fine tuning with RL. So one of the use cases that we have for LLMs that this work tries to solve is to build approaches that can utilize these LLM models as agents, meaning these LLMs accomplishing goal-directed tasks in open-ended scenarios, such as interacting with operating systems, interacting with certain databases, executing tasks that a human specifies to them, potentially learning more about the system by executing information gathering actions and stuff like that. This could also include dealing with shopping on the web or maybe controlling a device. There are many examples of this sort that exist out there. In all of these cases, you need these LLM models or need these LLM agents to sort of be goal-directed. So unlike sort of conversational systems where you can simply spit out a lot of text that seems to maximize your log probability under your model. For example, as you can see in this particular example that's showing up on the slide, in this setting of agents, you need the model to be to make targeted, precise actions, targeted, precise responses that accomplish the right possible thing and accomplish overall over a sequence of interaction, get you the task that you cared about. So this is called multi-turn reinforcement learning because you now are interacting over a sequence of turns, and in each turn, your goal is to sort of get to the targeted solution, targeted response, compared to sort of just saying vague things that would probably help the user in a conversational setting. So multi-turn RL is something that's crucial in this case because of these reasons. Prior work that tries to build multi-turn RL approaches actually is sort of bifurcated in a variety of approaches, and none of these approaches seem to address, or none of these approaches seem to have all the desiderata that you would need for a good approach. So for a good approach, you want to be able to learn from off-policy data during fine-tuning. You want to be able to deal with variable length utterances from the model. So in each interaction turn, your LLM could say sentences which are 1 word long, or it could say sentences that are 1,000 word long. You should be able to deal with doing RL like fine-tuning approaches, fine-tuning strategies in both of these cases effectively. And secondly, within the context of each utterance or each turn, which could be a variable length sequence of tokens, all these tokens need to be coherent with each other. They can't be arbitrary tokens that don't make sense together. Existing approaches that try to do multi-turn RL, they don't really have all of these three desiderata. So there are methods that would do RL or Q learning at the token level, meaning they consider each token as an action, and then they optimize for the model to produce the best possible token at a token by token basis. This approach has some pros. It gives you a very easy way to instantiate RL ideas in this context because it's a simple discrete action Q learning problem, but then it poses very long horizons, because if each token is an action, then imagine the set of all tokens that you are seeing in an interaction scenario, which will be huge. On the other hand, if you do turn level value function learning, meaning if you do each utterance is one action, you now have a variable length combinatorially large action space, which is again a problem for most RL methods. So there's no clear one single approach that does these all things well. And that was kind of one of the motivating factors that we had in this line of work. So what we started to do was to think about kind of building a flexible framework for doing RL, especially this multi-turn interactive RL, to train or to fine-tune language models, or to fine-tune just generally transformer-based models in general. And a starting point for doing this was to start with the designs that people have been using for single-turn RLHF, where you would train a reward model on some data and use it to train a policy. What we did was we said, well, you can replace this paradigm with a slightly different paradigm that I'm going to then generalize for multi-turn settings, which is this paradigm where you replace your reward model now with a value function, which is trained to approximate the long-term reward that you will get at the turn level. So for different utterances that you get. And your policy now is trying to optimize for the predictions of this value function. So it turns out that if you start from this and you think about this, building a solution concept along this sort of an idea, you can actually generalize this to a family of algorithms that we call Archer. And these algorithms are hierarchical RL algorithms. So here's how to view a hierarchy in this paradigm. You can think of the value function in this approach as essentially an off-policy RL algorithm that is operating at a coarser timescale of turns or of utterances. So this model is operating on a coarser action space where each action is a whole utterance output by a model. So a sequence of tokens that is output by your model that you're training. So this could use any off-policy RL method. And the policy in this case is essentially a low-level RL algorithm, for which each action is a token, and its goal is to optimize some reward targets set to it by the higher level RL algorithm, which is producing these value functions more generally. So here's a simple picture actually. So at the utterance level or the high level, you can train a value function that is supposedly capturing the long-term return to go over different turns of interaction. And then this utterance level value function sets terminal rewards for a lower level MDP, where you're trying to find actions, tokens that can optimize this terminal value function or terminal advantage under this value function. So it's simply a two-level problem where the higher level operates at a coarser timescale and the lower level operates at this finer token level timescale in this problem. You can also do this in many other ways. You can do a critic version of this as well, which we didn't explore so far. But basically, the idea is run updates at 2 timescales. And you can use your favorite algorithms for this. So you can use deep Q networks, your favorite offline RL approach for the critic or the utterance level, as well as for the policy gradient approach or the token level approach. You can use your favorite policy gradient method in this case. So with this, we actually found that we could get quite good results. So we had some very good results which compare So in a bunch of these language agent tasks, if you just take GPT-2 models, you find that Archer, shown in blue, actually gets you a much faster learning and much more stable learning than many other baselines. So this is in the online setting. You're interacting with the task, doing rollouts in this task, observing some reward feedback and learning from that feedback. It also works on tasks which involve shopping on the web, for example. This is a benchmark that was published in 2022. And it works better than if you were to use GPT 3.5 with expert prompting strategies. And note that here we are training a GPT-2 medium-sized model in this case. We also found that actually, because this paradigm is flexible in the sense that you can choose your favorite higher level algorithm for training a value function and your favorite lower level algorithm for training the policy, you can basically find that this approach will scale up to arbitrary model sizes. We know that we have done this work for RLHF once already, which is learning from human feedback. Potentially, we can use the same design details, the same infrastructure details for now scaling up multi-turn RL methods. So we did have some experiments scaling it up to 7 billion models where we see positive scaling. And also, secondly, like from an RL perspective, we have so much insight about which algorithms work better than others. Turns out that you can use the same insights and transfer them to this case, because now you have two RL algorithms, an off-policy method and an on-policy method operating at the two levels. You can swap them for the best possible design choices that you have, and that will work better in this case. So I had some more ablations here, but at a high level, basically, this is just simply a flexible framework that allows you to essentially deal with both the challenge of variable length action spaces, which can be combinatorially large, as well as long horizons, basically by decoupling them and using two different methods for solving these challenges independently, and they interact with each other. So that's sort of the high level approach for this work. There's many algorithms that we have not explored in this context. So this is a framework, really. You can choose your best possible algorithm for each of them. We haven't quite explored that, but I'm generally excited about this line of work, multi-turn RL in general, and how we can potentially use this for building a general recipe for transformer-based fine-tuning, transformer model fine-tuning, transformer policy fine-tuning in a variety of cases, even outside of LLMs altogether. So yeah, I think that was basically it. I think I went a little bit over time, and I apologize that this was kind of quite rushed, but I'm happy to stay around for a little bit and take questions. Yeah.
Yeah,
Yeah,
no,
thank you.
fantastic talk. I think let's thank the speaker first. And I think we'll probably have to invite you again to complete the second
Yeah.
part of the talk.
Yeah.
But I don't know if you have time for maybe squeezing in one question.
I think we can do a few questions. Yeah.
Yeah, okay. Any questions? Yeah.
So for the second part of the talk, when you were learning the value function and the Q function, did you still use the HL-Gauss loss, or was it the simple regression-based loss?
That's a good question. So it's right now it's a regression-based loss. So these two things were being done in parallel. I think that I see no reason for why we should still stick to using regression losses. So yeah, you're right. I think we should be doing that. Yeah.
Okay. Yeah.
Yeah. On the same slide, I had a question. Like when you are doing like two-level optimization, at utterance level, you are learning a value function of sorts and maybe state action value also. And at token level, you are summing up the advantages in calling like optimizing for that respect to the policy that you have learned. This looks very similar to the regret model based multi-step reinforcement learning that came from very recently, something like contrast to preference learning.
So I can I see. So I guess I'm not entirely sure what so I guess like I know about the contrastive preference learning work that came out. I think that the difference here is at a high level, I think this is prescribing an optimization strategy that is prescribing more like an optimization objective in my mind, at least. So in my mind, at least, like what the contrastive preference learning is showing is like how can you use preferences over actions over each turn actions to learn a value function. How can you convert preferences into a value function? And it does it with the DPO-esque losses, if I'm not wrong about that. I think that's kind of separate from figuring out the right optimization algorithm. So like in some ways, like here, the Bellman backup at the utterance level, this could be done with, like you can take preference data and convert it into a value function.
Yeah.
That's totally fine. Here I'm assuming that we had a reward function just because the tasks we consider are like that. But I think the key thing here is, do you do this at, like, do you learn a value function at the turn level, at the token level? Should you do which algorithm should you use at the token level for optimizing your tokens? So I think those kinds of design decisions, which are the optimizer choices or optimization procedure choices, are basically what we prescribe here. So you can, like, basically what I'm getting at is like CPL, and this is complementary in some ways. Like that prescribes a way to convert preferences to values. This is describing to you how to optimize reward in general with transformer models. Yeah.
Yeah. Thanks. Yeah.
Yeah, I actually had one question. I think one of the things you touched upon at the beginning was about sample efficiency.
Yeah.
So I'm wondering, like, with all these methods right now that you've described, how sample efficient are they? Because there might be domains where like collecting the rewards is extremely expensive also.
Yeah, that's a very good point. So I think in terms of sample efficiency, I think they are up to 20K trajectories. Each trajectory, you can think of it as about, so I guess like on the 20 questions and guess my city, these are tasks where, yeah, I guess I didn't describe what these tasks are. These tasks, here you're required to identify what the hidden intent of the other side is. So there's like a hidden word or a hidden city name. You can ask the questions to like elicit information about what the hidden word is using those questions. So in this case, the horizon is 20 for every task, and you are using about 20K trajectories on the guess my city and 80K on the 20 questions. So it's like about that times 20 many samples that you're seeing. I think clearly we can do much better if we than this. I think in general. So there's like, I'm not saying this is the final answer. I think this is just the starting point. In terms of wall clock time, that's maybe a bigger factor here, because when you take these transformer-based models and you need to do online RL with it, you're kind of sampling from the model, which takes time to sample. I think for that, it takes about, I think, 2 days or so for one run to finish for our experiments. They're not with a very sophisticated like model, very sophisticated model or very sophisticated compute cluster. So presumably, like I think a lot of those design decisions will affect the wall clock time as well. But I think certainly, like, I mean, if in the global scheme of things, I think this is probably the starting point more than like really amazing like endpoints.
Yeah, no, this sounds extremely impactful.
Yeah.
Thanks for this fantastic talk. It was really
Yeah,
nice.
and I'm sorry, I think I just packed up a lot of material. I think I probably should have realized, but yeah, I mean, this is
So
this is a very fresh work that I'm describing. So this is probably the first time I'm giving this talk. So yeah, if you have any questions, if anything was unclear, feel free to reach out, and I'm
fantastic.
happy to
Yeah,
talk about
we'll share across your email with people as well, so like people can reach out.